One of the nicest things about power series is that ultimately they're polynomials. If we look at a function that's set up as a power series, it's some coefficient times some power of x, just added over and over and over, which we can look at in this form: a0, a1x, a2x squared, a3x cubed, da 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 da, a to the n, x to the n, da 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 da, right? Why is that useful? Well, that's useful because the calculus of polynomials is super easy, right? It's always the power rule. If we take a derivative, we just bring down the power and subtract one from it. If we take the antiderivative, we add one to the power and divide by the new power, right? Polynomials are very, very easy to deal with. So if we have a power series of a function, we can easily find its derivative or its antiderivative using that power series format. So if I take f of x here, blah, 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 well, I know that f prime for this function, well, a0 derives to 0 because it's just a constant, and then a1x goes to a1, a2x squared, the 2 comes down, and we subtract 1 from the power. The 3 comes down, we subtract 1 from the power. The n comes down, we subtract 1 from the power, and so on and so forth. So what that tells me, this term right here really is the kicker, because if that's the regular term and that's the generic version of a derivative term, then we can pop that in right there. So automatically, if I have a power series that looks like this, I have a derivative of the power series that looks like that. Very, very clean, very, very easy. You also will sometimes see it written like this. The reason why is because notice that this starts at 0 and this starts at 1, because we eliminated the first or the 0th term, right, by that derivative. So we could start this at 0, but if you did, notice that when you plug in 0 here, this whole term just disappears because n is equal to 0. So generally speaking, this series is written starting at 1. Some people prefer it to start back at 0, so they do a reindexing. This is perfectly fine. There's nothing wrong with it. It's just a different way of doing the same thing. But this is the typical way that we'll deal with it. Now for the antiderivative, you still have the same idea. If we have this original function, well, we get a c. We always get that arbitrary constant when we take the antiderivative. And then a0 gets a0x. On this one we add 1 to the power, divide by the new power. On this one we add 1 to the power, divide by the new power. And then I guess I didn't have one for here, but the arbitrary term, we add 1 to the power and divide by the new power. So the idea here is we're doing the power rule for antiderivatives over and over and over, right? Nothing new here. What that gives us is that this constant and we kind of have to separate this out because it's not really an a something, it's just some arbitrary c. You theoretically could call that like a -1, but you typically don't see that at this level written that way. So we take what's left over here and we take the generic version of the form, take the original sequence term divided by the new power and add 1 to the power. So notice how these are related. If I look here and here, I take the exact same thing except I add 1 to the power, divide by the new power. Nothing, it's literally the idea of the power rule. Add 1 to the power, divide by the new power. And you do it for every term. So you don't have to overthink it. It's a very nice, compact, convenient form. This is super important. This has way more importance than it probably seems like right now, because there are certain functions for which an antiderivative is just not readily available. For instance, e to the negative x squared. There is no generic antiderivative available. If you find one, let me know. I'll cut you a deal. But that's not well known. But we can develop a power series for e to the negative x squared, which means we can write its antiderivative in this infinite series form. And since we can know where the infinite series is going to converge, we can say, okay, well, I'm going to run 10,000 terms of this series. And it's not going to be perfect, but it's going to be close enough for any value that I plug in for it. And so there are a lot of real world applications of this. This is very, very powerful. This is useful, no doubt about it. But derivatives of functions are generally easy to find. antiderivatives are not generally easy to find. This is a very powerful technique here. So now notice I did this for the that Maclaurin style series where the series is centered, or the Maclaurin polynomial where it's centered at 0. But this can be generalized to any power series centered at c. The difference here is that you'd have x minus c to the n, x minus c, x minus c. Like, it's not really that different, but I didn't want to complicate it by doing a general centered series. So what we can do is we can apply this to something we've already discussed, the idea of this geometric series. We have, okay, the a is 3, r is x over 2, so we automatically know we can generate a geometric series that looks like this: a times r to the n. Now what I also did is I distributed x to, or that nth power, so I have x to the n divided by 2 to the n, and I split that off. The reason I want to split that off is because now I have some sort of a sub n term, 3 over 2 to the n times x to the n. So this is a to the n times x to the n. That's useful because notice all of our formulae use a to the n and a to the n. So now I can take the derivative. I can say, f prime is 3 times n over 2 to the n x to the n minus 1. So again, I'm following my formula. I'm multiplying n, and I subtract 1 from the power. I'm multiplying n, I subtract 1 from the power. When I take the antiderivative, I have a sub n, add 1 to the power, divide by the new power. Add 1 to the power, divide by the new power, leave that alone, add that plus c there. And that's it. You now have an antiderivative. Now, and this may or may not be as useful as you want it to be, and that's fine. And for these, it's probably not that useful because, right, you could find the antiderivative and derivative of these very easily. So you might ask yourself, why should I do this? And that's a reasonable question. But this is showing the technique so that when we get to things that we need it for, we're prepared to do it.